Jayaram that is in the audience as well, and he was an ex-Monash, and Mark Curtis and Alan Protan from the Bureau of Meteorology, also Dr. Alan Seed from Griffin University. So the topic that I want to show you today is how we are doing rainfall, or what we're doing rainfall forecasting at the Bureau of Meteorology, and how we can planning to use machine learning or deep learning to enhance that one. So next slide, please. So probably you are aware that Australia has a really large network of weather radars. Also, that image of pixels moving across the space that sometimes you see on the news, but also you can get it on the mobile. So one tip for you is we have 61 weather radars, and that makes Australia probably the country with the highest number of radars per capita. There are more radars in America and China and Europe, but we are only 24 million here, and we have 61. That's a lot of radars. The important thing here is the Bureau processes all this information and publish on the website, and everything is fine. But all this information is observed rainfall. That's what happened in the past, or what the radars were seeing the thing. And what we want to tell you guys is, if you are gonna go out to the street, for example, and answer that question is, may I grab an umbrella or not? Or I need to go to a run. I should be just wait 5 seconds or 10 minutes or 30 minutes, or short my run for half an hour because I know that it's going to be in the rain. And that's why we call it nowcasting. So then next, please. And that's an example of next thing. So basically what we have is, well, nowcasting, the previous one. But the nowcasting, can you go to the previous one? Yeah, fantastic. What we call it nowcasting is very short-term forecasting. So what is going to happen in the next few 10, 20, or 30 minutes or 1 hour ahead. So the example that I'm showing you at the right, so how that works, the nowcasting. Basically, what we have is the last few observations from the radar, and then based on that observations, we predict how the rainfall fields are going to move into the future, right? It's a lot more simpler than to say that one that actually do it, because our final goal is actually that the forecast rainfall, the forecast fields that come in from the observations looks identical or very similar to the observations, right? The panel at the right, the animation that I'm showing you is, I am showing you for the city of Melbourne, one animation from observed rainfalls that becomes a forecast rainfall, right? So 60 minutes of observed rainfall that then becomes 60 minutes of forecast rainfall, right? If you cannot see the transition between observed and forecast, that means that our team is doing a really good job. And because the characteristics, the texture, and all the full resolution of the radar is preserved on the future, on the forecast rainfall, that's a good thing. We use a system called short-term ensemble prediction system. So it's not based on machine learning; it's based on physics and statistics, and they're all good science, or good science, all and good science. But the interesting thing is we are able to run in very, very short latencies. What it means is we have a new rainfall observation or a map every 5 minutes, and we are able to generate an ensemble, a collection of possible future forecasts from 0 to 90 minutes every 5 minutes in seconds. So that's why we are not being in machine learning, because our solution is really fast and really, really massive. So the other thing, and you can go to the next slide, is we provide not just one possible scenario in the future, possible forecast, but an ensemble of forecasts. And this is an example of a radar in Cairns, in the north of Queensland. And what you can see as you follow the labels is an animation between 0 up to 90 minutes. And from the top left is the observed rainfall, and then the ensemble mean, a percentiles calculated from the ensemble, and 4 or 5 different members of the same ensemble. So the most interesting thing here is all the fields that are forecast look quite similar, right? But they are different. It's like a little cut that they look similar, but they are all different. exactly the same idea. So how we are going to be using, next slide, please. So the ability to be able to produce the forecast rainfall and do it in seconds allows the Bureau of Meteorology to do national predictions for every single radar that we have in the network. And this is an example that we are testing and we are really, really close to go live. So we are able to predict from 0 to 90 minutes for every single radar in the country and generate this map. So that hopefully will come very soon in your mobile bomb applications, and you will be able to go out, or before to go out to the street, check if there's going to be any rain in the next hour or 90 minutes. Anyway, how we are using NCI, so next slide, is we did an extensive verification. We call it steps. Like we use 47,000 5 minutes, 256 by 256 kilometers rainfall, and we verify that it's really good and it works really well, and it's much better to the old system and much better to the open source reference implementation. However, we are not using machine learning, so all this analysis that we did was fantastically done in NCI, and we're still working on that. But we are not using machine learning. But we know that there's a lot of interest in machine learning. So next slide, please. So one good thing that, I'm done machine learning. One good thing that we have happening is we help also to develop an open source steps, and this becomes in Python. So this becomes the gold standard for precipitation nowcasting. And you are more involved on machine learning than myself, of deep learning, and it has been a numerous papers and research happening about precipitation nowcasting. That one in particular, Nature, was quite popular, but I just Googled the last month of nowcasting deep learning, as you can see on the right, and I found 151 results just this year. So the good thing that we have is we have data on the NCI, we have an open source software that will be able to replicate that one. Despite of our efforts and our application is really good and it performs really well, there's many things that we can improve, and that's where we believe that machine learning will help us. So next slide, please. And so one thing before to go to the next slide is most of these, thank you, most of these machine learnings or predictions that you see nowcasting are really good to predict rainfall fields with low mean square error, but are not that good to predict a rainfall fields that looks like a rain. So what happened is all the machine learners are really good to minimize the mean square error, and that means that they will be super smooth, but they will not look like a radar or a rainfall. And therefore, instead to be able to tell you this is going to rain in your house, probably will tell you this is going to be rain in your city, and probably that's not good enough. So anyway, but back to the connection. So we believe that we can connect machine learning and or implementation of the steps and different options. One thing is, of course, develop better ways to use deep learning to match the quality of the step-by-step prediction, the standard approach, the gold standard approach. But also, we believe that deep learning may help us to run the steps nowcasting on the short-term sample for them to identify cases where additional information may be required to produce a better forecast, like a grow or decay effect of the rainfall, or orographic enhancements, or effect of the sea, etc., etc. But also, what we can think is if a deep learning network use the input of the nowcasting from the rainfall nowcasting, they potentially will be able to identify the chance of heavy rain or hail or flash flooding and generate like a kind of pseudo alert or warnings, right? And also there are many other options, like take the satellite-based rainfall estimations and pass through the network and generate a radar-like rainfall fields. Anyway, there's a few four or five things that we are thinking. Basically, our idea to participate here is we are open to explore academic collaboration with Monash or with anyone else. And if you need more details in the next slide, or you want to contact me in the next slide, is our contact details or questions in the chat. And thank you. And I hope that was 10 minutes.
You made it in your 10 minutes. We know who to complain to if the app doesn't work very well when the updates come through, so that's good. I will ask questions in the chat because we are right on the 10-minute border. I'll stop sharing my screen and hand over to Fred Fung to talk about machine learning HPC applications at the NCI.
Hello, everyone. I'll just share my screen real quick. Okay. Can everyone see my screen now?
Yes, yes, we can see.
Yep, sweet. So yeah, hello everyone. I'm Fred Fung. I'm working here in ACI in the training team. I'm a training officer in NCI. So today I'll just talk about the machine learning. So to justify this terminology, when I use machine learning, that really means a broader AI machine learning applications. Running those applications HPC systems. So I have to say I'm not a real machine learning expert. So and I'd like to share my point of view from a host facility, supercomputing facilities perspective. So from the host facility perspective, machine learning applications is have the similar challenges as other scientific softwares. So those are the performance, so measured by how many petaflops, sorry, not petaflops. So the flops and the portability. So a lot of our developers developing their applications from their own desktop or different systems. And now they want to run it on the HPC system. So how easily can that be compiled or run on the HPC system? And the next question is about the productivity. So especially this is concerning the machine learning, where you have to prepare data and then train your data, and maybe later stage you have to visualize your output. So those are the three key challenges, well, I guess, present in most of the HPC applications softwares. So to achieve those three goals, performance, portability, and productivity, the machine learning applications we can try to improve this from two categories. One is on the left, the machine learning aspects, and as well as from HPC aspects. So from machine learning aspects, I'd like to start with theory. So a lot of us, so when we run we used to at NCI, we run a lot of machine learning training sessions. And one thing we observe is on top of the softwares the practitioners need to learn, we kind of ignore the theory of the machine learnings, the theory of artificial intelligence. And they sometimes will hinder the development of the softwares. I'm not saying we should, as I outlined here, we should, as practitioners, care too much about the theory, but at least we need to learn some basics. For example, the loss functions, optimizations, optimizers, and so those sort of basic ideas to help to stay less error prone. For example, if your example is, so if your training model is a regression predictive modeling, then you probably want to choose the regression loss functions, as this is measuring basically the L2 norm. If your model is a classification, then you probably want to choose cross entropy loss functions, as you essentially are measuring the L infinity norm of your loss. So yeah, so here I have a figure here. So we have to on the one hand, we do the practitioners, but we have to be abreast with the theories. For example, here's at least this one is a 100 pages paper proving it, just a simple convergence proof of gradient descent methods using in the artificial neural network with special targeted functions. I think the target functions are so special, so they're just linear functions. So we do have those theories there. So this is something I'm just personally, because this is a kind of like forum discussion. So this is something I think that'll be nice to sort of emphasize when we provide machine learning trainings. My personal perspective, just provided some theory background for the trainees. So another thing, and so second aspect from machine learning is the programming model. So I'd like to view machine learning programs as a GPU accelerated application. So this is very general from the host facility perspective. So machine learning is probably no more than another GPU accelerated application. So this is very dependent on the hardwares. So different systems will have different hardwares. For example, you have your Apple laptop. He has his Dell laptop. They're running on different chips, different GPUs. Same thing in the high supercomputer facilities. On Gaudi, so this is the system we currently have. At NCI, we have NVIDIA GPUs at this moment. So naturally, the CUDA, OpenACC, OpenMP, or OpenCL will be the natural way to program. So if you're familiar with the SQL or Data C++, stands for Data Parallel C++, those standards, and those are not well accepted on our machine. But different machines, if you want to do machines, take your code to the Oak Ridge's Frontier, Pulse's machine, then you will get a different color scheme here because they essentially have a different hardwares. So for programmers, I just like to build this awareness that you have to be aware the very underlying system could be very different. So most of us probably work on a high level. So we work on directly with the routines provided by PyTorch or TensorFlow for those programs. But what really matters, so now I'm talking about the performance. So what really matters for the performance for this AI programs is the underlying this thing called GEM. So basically, this is routine general matrix to matrix multiplication. So this is the sort of the core of your this routine core and the low-level routines from TensorFlow to enable you to do the matrix multiplications very quick. So this is a part of the routine from BLAS, and different standards, they have different implementations of BLAS. For example, CUDA has cool BLAS, and I think one API, the Intel thing, has their own implementation in probably one, so their neural network packages. So they have different implementations of their BLAS libraries. Therefore, your performance of GEM will probably be affected. Whether it's significant or not, you have to do a test, but just be aware, depending on different system, although on the high level, you're using the same package, but on the low level, it's actually probably executed differently. So for quite a extreme example, if you are using untuned OpenCL implementation for GEM, I've read paper this actually had done benchmark, you will get a very bad performance. Just for an extreme example, I guess probably not many people doing AI machine learning program with OpenCL anyway. So yeah, like what I mentioned before, Gaudi, the system here in NCI, we have NVIDIA GPUs, but it's not always the case worldwide. Like what I just mentioned, different systems, they have different hardwares. So another thing, so now I'm moving to this right side of aspects of the HPC. So there's two sort of things practitioners need to be aware of once the I/O, so data loading, sometimes can be the bottleneck of applications, especially a very large training set. And now the one is the parallelization. So how to actually use multiple GPUs. So those will be, these are the targeting things I think we need to be versed into. And my colleague Ben will talk a bit more about I/O, I think, later in his talk. So yeah, that's all about my quick presentation. So I would like to bring up this discussion as the purpose of this forum, this meeting. So we see Intel now is pushing the open API, and we see some computing facilities have already started using AMD GPUs, and I wonder how would this change the landscape of the currently CUDA-dominated AI programs. Okay, that's all about my presentation.
Thank you for that, Fred. As much as I want to sit here and dig into what you've got up on the slide here, I'd love to hear more in the chat, and maybe we'll re-ask this later in question time. And I'll hand over to Brent Gardner, who's going to talk to us about example workflows for doing machine learning on HPC.
Hello. You can hear me all? It's all good? Excellent, excellent. Now let me click the button so you can see the things. Not that one. This one. All good?
I can see it. Awesome.
Excellent. And so thanks for that. And I guess who I am. I'm the machine learning tech lead at CSIRO, which means I'm a user of the resources as well as helping others to use them, and kind of that involves like training and mentoring of the researchers and practitioners and staff. And that could be new to data analytics and ML, or they could be wanting to branch out and explore more things and just do more neat things. And I'm here to help them do that and empower them in all those things. And that also involves finding like easy and effective ways for them to do that stuff. And so I'll go into, like, that leads into what like the motivation behind giving this example workflow for doing ML on HPC. So it's what we have, and this is going to be largely about what we have at CSIRO, but it's going to be applicable, it will probably be applicable to other things, and that's going to be in this more general way. And so we have this Kubernetes, like a small Kubernetes cluster on a couple of DGX boxes that has V100s in them. And that has it's a containerized solution running Jupyter Lab with a GPU behind it. And so we have this, and that means the user, because it's in this containerized kind of environment, they have the freedom to do whatever they want as far as install things, play, break it, do whatever they want. And if they do something silly and break it and do that, they can stop the server, restart it, they get a new fresh container from the image, and they can do it all over again. And being a Jupyter Lab environment means that it's familiar to lots of people, because, as you know, like, that's the way a lot of people are training and learning, and the way you present things, and you can play, and it's all the good things. And so it's very familiar and easy for people to do, especially for new users. And in the environment that we have, we can invite other people in to that space and share that with each other. So it's very good for like collaboration or training, mentoring, all of that kind of thing, because not everybody, it's the people that you grant access to can come in and do stuff. And so it's like the collaborating with researchers part, invite others, and then it's just a good environment to prototype and play and do all the things. Saying that, it is limited in resources because it is a small Kubernetes thing with it's not as big as HPC. So then HPC, it's Bracewell that we have has 456 P100s, lots of, I think it's like just under 4,000 compute cores, blah, blah, blah. It's an HPC thing with lots of resources. And it has like the modules you load. It's the normal, like you load modules, you do things, and then you can talk with the admins to get a new module created for you after you figure out what you want in the Jupyter environment that you've probably broken a few times and restarted and done that. So it's, you can say, this is the environment I need, and if it's within reason and that sort of thing, then you can go to the admins and they create that for you. And so it's the easy part here is like you need more resources. You just, in your batch script, you say more please, and it's like, okay. And it's because there's more resources, and there's, you know, like it's not a hack, but it's like the thing of just split it up into multiple things and just submit 100 jobs instead of submitting one giant job. And so then that kind of, you don't skip the queue, but you go into the shorter queue. That's just kind of a, if you didn't know, you're welcome, I suppose. So that's kind of the two environments that we have. The main thing here, the key, is that the same data store is mounted on both. So that makes it very easy, very well protected. It makes it very easy to bounce between the two systems with your data. And so the workflow part could be, they go into Jupyter Lab, and they have their data sitting there, and they can do their data exploration and the visualization and all of that, where it's, the interactive environment is good for that. And then you do the data prep and the feature engineering and all of these things, because you can do Jupyter things. You can do easy code testing, model analysis, do all of these things. The model analysis could come at the end, whatever. The order doesn't matter, because the data is in the same place. You can do all the things. So it's kind of, once you get all of the stuff set up at the beginning, all of kind of, you figure out what you want to do, then you jump over to HPC, which could be go to a different window. Everything's still sitting there. The only trick may be you have to do your script a little differently and put it into a script instead of having it in your cells. But that's much easier than trying to use HPC in an interactive way. And then, so if you have, let's say, large data that's going to be very computationally expensive to process, then you can go to HPC and do it there using Dask or whatever other parallel way of doing it. The hyperparameter tuning, just like saying before, submit 100 jobs of all the different things, do these things, you get the results back quicker than waiting 2 days to try all of if you want to do an exhaustive grid search or blah, whatever. And then the training, and then you can just do the training there, and then you have your model. Then you can jump back to Jupyter if you want to do some interactive stuff, to do some explainable things and look at maybe some activation maps or whatever. Then play with this and do the viz again, and you can just keep going back and forth. And as it's an iterative process anyway, you'll be going back and forth and around in circles to do all of the stuff and play. But it's something that's kind of like the path of least resistance. Is this was kind of born out of, these are the resources we have, and this is kind of just so if you're in like walking on a trail and you're like, oh, there's this trail where the animals go, well, that's probably going to be the easiest way to walk because they figured it out. This is a way to use the resources that we have. And it is on a Kubernetes cluster, and it is like this special thing, but that's not the important part. The important part is there's this interactive thing that's friendly. The data is mounted there. You have the HPC system, which is less friendly, but to do a batch job, to submit to the scheduler is quite simple. The data being mounted on both makes that easy, I think, as far as it makes it much easier than trying to do any one thing on the two separately. And that's really all. I mean, I probably could talk for hours about the same thing, but it's really about it. So thank you very much.
Thank you, Brent. I will release people to a 5-minute break if you want to jump up and grab a coffee and stretch your legs and join us back here at 2 o'clock. I've learnt that long Zoom meetings are easier with breaks. So come back at 2 and I will introduce you to our next speakers. right, that's my 5-minute timer going ding, 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 ding. Welcome back, everybody. I see Brent is getting grilled with questions, such as the case when you bring up machine learning on Jupyter Notebooks and HPC. I've been there. I'm going to hand over to Tim Carreria-Paul, who's with us. I'm not sure if his other project members are with us today, but I'll let you share your screen, Tim.
Yeah, great. Thanks, Kiowa. It will, in fact, be me today. So let's get started. All right, so where's the button to start the slides? Who knows?
Up in the top right, the slideshow button.
Oh, of course.
I think it's moved a few times and changed names. So.
Great. Well, yeah, thanks for being here today, everyone. My name is Tim, and Kiowa was actually the project manager for this project. I've got a few other group members as well. So we've got Davide, who was our project lead, but he's unavailable. We've also had Cleo Vernon and Nguyen. So I'd also like to acknowledge the fact that I'm just one of a team of members that worked on this. So for a bit of background on this Horovod project, this is a part of the Environments for Accelerating Machine Learning-based Discovery initiative, which one of the things that initiative aims to do is provide tools for HPC systems for machine learning researchers to use. And as such, Horovod, being a distributed deep learning framework, is like very useful. So Horovod provides the ability to scale up any existing code you've got, whether that be TensorFlow, PyTorch, Keras, or MXNet. And it enables, with just a few extra lines that you can pretty much copy and paste into your code, enables your existing scripts to scale up onto a HPC system efficiently. So yeah, with that in mind, what exactly is Horovod? So as I've just explained, it enables your code to scale, and it does this by running an identical copy of your code on each GPU that you've got available. So in this example, we can see 8 GPUs in total, and each of those will be pins to a process. And also you could have, this be on a single node or multiple nodes. And Horovod works by distributing the training data across each of these identical copies on each process. So, let's say you've got 8 GPUs and 8 processors in this example, your data set would essentially be split into 8, and 1/8 would go through each copy. So a bit more on how this works in a bit more detail. So our processes will be identified by global ranks and local ranks. And the values of the gradients during training need to be shared between each of these processes for, training to scale. And this can be done either with the all-reduce algorithm or the ring all-reduce algorithm. Now, the all-reduce algorithm is not very efficient, as it can cause bottlenecks. If we're looking at this image on the right here, we can see we've got a single process which is responsible for reducing, and let's say in this example, we've got 5 GPUs, but you can imagine, with 10 or 20 GPUs, there would be a very significant bottleneck occurring there that would slow down our training time. So instead, Horovod uses ring or reduce, which shares the gradient, the gradients in a circular manner. So this eliminates all bottlenecks. So each GPU, or each process, would communicate simply to its direct neighbor in a circular fashion. And this eliminates any possibility of bottlenecks while you're scaling onto multiple GPUs. So what was the goals for these projects, now that I've explained a bit about how Horovod works? So obviously implementing it on Massive, or M3, which is the 3rd version of Massive. Running some models across multiple nodes and multiple GPUs to make sure it works. Carry out some performance testing and benchmarking, and then finalizing this project by producing documentation and resources so that Horovod is available and easily accessible for anyone that uses M3 to utilize. So our current progress, pretty much just a rehash of what I just said. So we've set up a Horovod environment environment on M3. We've used the horovod run command to use horovod. So horovod run is, as the name might imply for some of you, a wrapper for MPI run. Yeah, so if you're familiar with MPI run, you should have an idea intuitively of how horovod run works. Also things like using TensorBoard and horovod timeline for model tracking and model optimization, and also performance testing on our M3's ImageNet dataset as a benchmark. So here's an example of horovod run working. So we can take any existing code that runs on a single machine and easily scale it up. So whether this be for TensorFlow, Keras, PyTorch, or MXNet. We simply edit our code by adding a few lines, which if you go to the horovod docs website, it's very simple. It's pretty much plug and play. And once you've made those edits to your code, which can run on a single machine, it can easily, it can effectively scale onto a HPC with like any number of processors and GPUs. So to run a horovod script, well, to run horovod on a training script, it'd just be, horovod run and then the path to the script. And we can see a bit of job data of an example of horovod run working. So in this example, it's very simple. We did it around the beginning of this project. It's just 2 nodes and 4 GPUs. And here's an example of the execution. So in terms of concluding the project now, what we want to do is we want to make sure that horovod works well with M3's new partitions. So M3 has recently received an upgrade over the holiday period, and we want to make sure that no bugs arise. So if any do, we'll need to stay on top of that. And finally, we want to publish documentation on M3's docs page. So this will enable the M3 community to be aware that horovod's available and that they can use it to accelerate their deep learning training, regardless of the framework they use. And we want to make this as easy as possible. So we'll be also making available some template scripts. So this will be like, for example, a TensorFlow script that has those 6 extra lines already included, so that if you've never used horovod before, you literally don't even need to, invest time in understanding how it works. It can just be available for you. So, you don't need to spend time worrying about how, to use TF distribute, for example, or even horovod. You can just take the code from the docs page or wherever it's available on Massive and plug and play with just putting in your own code. And this should make horovod as useful to as many people as possible on Massive. Without requiring like any effort really. Well, that's the intention. So with that, that is the end of this presentation really. I'd like to give a special thanks to the following people. So Suhag, Chris Hines, Oliver Cancross. So he was from the University of Queensland and he really helped us out getting this off the ground. They also have horovod working on the UQ cluster. I believe it's called Weiner. And then obviously for Kiowa for managing this project. So yeah, thank you for all your help and support. And I guess on a final note, I could also say if any of you guys are interested in getting horovod installed on your HPC systems or the one that you use, probably get in contact with Kiowa or Oliver Cancross. So yeah, thank you all for listening.
Thank you for that, Tim. I'm aware we're running close on the time, so I'll get questions in the chat. I'd love to hear from other admins at some point about how they're running horovod on their cluster and how their users are going, adopting it. It's not as straightforward as Tim's lovely short presentation made it out to be, in my experience. Thank you so much. I'd like to hand over to Samitha Hereth to give the next presentation. I think you'll be able to share your screen. I can't wait to see what we're learning about today.
Thanks, Kiowa. I hope you guys can see my screen.
Okay.
let me start the slideshow. Actually, yeah, I'm Samit Herat, and I'm representing, the Vision and Language Group of Faculty of IT, Monash University. Actually, yeah, today I'm going to give you guys a very high-level presentation of like how NCI Gadi has been helpful for us, like for our group, our PhD students to get their PhDs done, and also like for us to cover like our project deliverables. So yeah, so this is going to be covering that aspect actually. So so we are a subgroup of Vision and Language Group in Faculty of IT in Monash University, and we are about like 20 members. So we are led by Associate Professor Gholamreza Hafari, and like our work is like primarily focused on like a fundamental research related to computer vision, natural language processing, and like a multimodal learning from vision, both vision and language. Now, as I said, like our work is mostly like on these topics, and because of this, our work is like entirely like on deep learning, and we are like a heavy consumers of like a GPU resources. Now, as of like for this period, like we were from January 2020 to December 2021, we were supported by Monash Gadi partnership, and these were the our like main resources during this time. Like we had Gadi, like a very valuable resource for us, and the other resources were like we had allocations from M3. And also like we had our own Slum cluster, like with 24 GPUs. And we had also GPU allocations from like project facilitators, like mainly DARPA. So, but anyway, like I mean, Gadi has been like a very helpful, useful resource during this period. So like I'm going to take you through how Gadi helped us. Like so we yeah, like we use Gadi mainly for our project like learning with less labeling. This is a project funded by DARPA, and like in this project, like I mean, we are competing with other participants of the this project were like UC Berkeley, IBM, Intel. These people, and they are. It's needless to say that they are like with a very rich resources. So like yeah, so and we had our resources. So like with these resources, we were able to like our students and like they're able to make submissions to top tier conferences, CPR, EMNLP, CCV, and like make publications there. And also like we were like with these resources, we were able to like cover like our project deliverables. Like for example, we submitted 3 software systems in 2020, and like we submitted like 4 systems in 2021. Now I'll take you through some high level like material like on like our what our students like group members have been working on. This is one project like this is led by Islam Nasa, a second year PhD student. This work was accepted for CVPR 2020, published in CPR 2021. This was on semi-supervised learning. This was improving like upon the state-of-the-art fixed match methods, and now we obtain very decent performance. These are some numbers. I'll skip them in the interest of time, but you are welcome to look at our papers. And also like we are currently working, we were on this period like working on extending this to more computationally exhaustive problems such as object detection, video classification, and like also we are doing algorithmic improvements. And again, like with another Sean Lee was also like a student that who just presented his final presentation last week, and he's mostly working. He's working on language domain, and these are some publications like he made like with the help of Gadi. So this is his work on intellectual property protection, and also like this is his work on like this paper is still in review for knowledge distillation. Now, sorry, I'm sorry for running through these tables in the interest of time. So now, again, like so these were like achievements of our students, like in their for their PhDs, how Gaudi helped, and like also like this Gaudi helped, like as I said, to cover like our project deliverables. For example, for this dark file WLL project, like I mean, this was a two-phase project. Like in October-December period, like we made like 3 system submissions, as I mentioned, and like based on the performance of our systems, like we were chosen to participate for the next 1.5 years in the phase 2 of the project. And now we are also like like last year made like 4 system submissions, like including this additional video classification problem, like which is like heavily heavily GPU consuming tasks. Like so we were able to cover these things with our resources, especially like Gaudi. So yeah, I mean, we like to express our gratitude to Gaudi and it's all these facilitators for these providing us these resources. Yeah, that's thank you.
Shockingly enough, you've got a couple of minutes left. So if anyone has some exciting questions, we can ask them in the next 3 minutes.
Yes, please feel free to ask any questions about our work.
All right, people might be frantically typing in the chat instead or saving it to the end. So what I might do is hand over to Ben Menadue, who's going to be talking to us about machine learning on HPC from a sysadmin's perspective. I'm very keen to hear this. I've been looking forward to this since I saw that that was the title of the talk. Over to you.
I'll try not to disappoint then. So thanks for the introduction. I'm Ben Menadue. I'm on the HPC team at NCI. So I look after the HPC cluster that we have. Today I just want to give you, I don't know how familiar everyone in the meeting is with NCI. So I'm just going to give you a brief intro of what hardware we actually have, and then some high-level details about what we see with machine learning running on the system. So we deliberately aren't particularly invasive with jobs. So from an administrator's perspective, if it's working and the user's not complaining, we don't ever see what's happening. So some of these ideas are just what people have complained about rather than necessarily being truly representative, but the things just to keep in mind. So if you don't know who NCI is, we're at ANU, that's our building. We're a collaboration between universities and government organizations. So if you're in Australia and a researcher, there's probably some way you can get access to our systems. We have significant compute and storage capabilities. We have a 20 petaflop supercomputer called Gaudi. We have 50 petabytes of high performance storage, and we have a fairly extensive cloud system. And all of those are connected together with a high performance network. So you can access your data that's on that persistent storage on either the cloud or the HPC system. So just for the pictures, that's sort of a map of the NCI facilities with our, how do I point? Can people see my cursor? Yep. So, we've got our storage systems, and then they're presented the NFS out to the cloud or as lust amounts over onto the HPC cluster. So that's, all put together like that means you can run things on the cloud and the HPC cluster and have them integrate together, which is, I'll come back to later, and I think other people have touched on as well, but that sort of marries nice with machine learning type workflows. So in Gaudi, if you want to do machine learning, you're probably going to be doing your training on our GPU nodes. Where else do people do training? We have 160 of them. They have some fairly powerful CPUs in them, not that you'll be using them much. And then each has 4 NVIDIA V100s there. Someone said before the 32 gig ones. And to answer a question someone had in the chat, they've got an all-to-all NVLink network between the GPUs inside a node. There's 384 gigabytes of RAM in each of these GPU nodes. So that gives you a fair amount if you wanted to load all your data in at once. And then they have 100 gigabit a second connectivity to Gaudi's fabric for both the storage and for talking to other nodes if you're doing a multi-node job. If you're trying to do inferencing, you don't need to use the GPUs. Our CPU nodes, and there are a lot more of them, there's 3,000 plain CPU nodes. They've got some even more powerful CPUs in them, and these being Cascade Lake have Intel's vector neural net instructions available on them, which are specifically designed for inferencing neural networks without needing to use GPUs. These only have 192 gig RAM, but that's probably still more than enough for a lot of people. And again, they're connected to Gaudi's InfiniBand fabric. Next up, storage. To put it all together, Gaudi has 2 scratch file systems. What's an SSD is like a gigabyte a second. These scratch file systems can do about 500 gigabytes a second, read and write sustained. And then we have our GData global file systems. As I said before, there's 50 petabytes total, and they're typically 100 to 150 gigabytes a second. So in terms of raw IO bandwidth, there's a lot available there. And if you're loading, terabytes of data in, you can probably get it in pretty quickly. And then each of the compute nodes in Gaudi has its own internal SSD if you need to do some sort of job-specific temporary storage for saving things out and loading it back up. So some people were talking earlier on about running things on their workstation and running out of resources there. How does a supercomputer differ here? Supercomputers get their performance through large amounts of parallelism. An individual GPU, it's the same speed. You take a V100 and stick it in your desktop, it's the same speed as if you stick it in a HPC cluster. It's only because the supercomputer has lots of them that it's fast. And the same thing about the CPUs. Lots of cores, but they actually may be even slower than what's in your desktop machine. And one of the things people have complained about is that their jobs run slower on the cluster than they do on their desktop machine, putting aside fitting into memory or not. And that's simply because they haven't taken advantage of that parallelism. So if you're writing a machine learning workflow, pick a framework that, when you start, if you do this right from the start, it's a lot easier than trying to change halfway through, but pick a framework that supports parallelism. Multi-GPU within a single node, I think most of the frameworks have that automatically. And then multi-node parallelism if you want to really scale up. So someone spoke about Horovod before, and I think there's a couple of other similar frameworks out there. But another way you can also parallelize is doing your hyperparameter tuning and run thousands of jobs almost concurrently, testing out every possible set of hyperparameters. I think I'm touching on a lot of what everyone else has already said. Storage in the HPC cluster. Lustre is designed for storing large files and reading them and writing them in large blocks. using a large clustered file system like Lustre, you get a consistent view of the file system across everything it's mounted on, so thousands of nodes. But maintaining that consistent view means there's some locking overhead whenever you want to do something. So it's especially noticeable for metadata-like operations, so opening and closing and statting and renaming, everything like that. That's where you really notice it. And the actual raw bulk object storage is just good old-fashioned spinning Rust. You can't beat that for, cost to gigabytes. But that means that random I/O performance is not that great because, you've got, if you want to try and seek around in the file, you've got to move the heads around on the disk, and that takes milliseconds to do. So generally avoid that. Unfortunately, machine learning, a lot of the example codes and people start with, they just read in a set of JPEG files from disk. If they're looking at images, that's fine from your local SSD because it's local and there's no locking or anything like that. That's almost the worst way to do it on a HPC cluster. So, if you have 1,000 files and you want to read them in multiple times to do, say, hyperparameter search with different jobs, consider bundling them all into a single file. And don't do JPEG compress them, store them as bitmaps or something like that, because that way you can just load the entire file at once. There's no overhead from needing to open and close those thousands of files. And if you've decompressed them, so they're all bitmaps, they're all the same size, makes it really easy to load them in parallel. And again, 100 gigabytes a second of storage bandwidth, you only get that if you're accessing it in parallel. Workflows on supercomputers. That's another point of contention with a lot of new people with machine learning that have moved over to Gaudi. Our OS and our job scheduler is designed for effectively standalone, completely isolated batch jobs. So inside a job running on the system, there's limited interactivity. You normally just submit a job and it'll run sometime in the future when those resources are available. You don't normally interact with it. And there's limited connectivity. There's no access to anything outside of the cluster from the compute nodes, apart from that storage that's mounted directly there. And the HPC system, as opposed to running on a cloud where there's probably oversubscription and someone else might be using the same CPUs at the same time as you, on the HPC, you have dedicated access to those resources. While your job is running, nothing else will even know about those CPUs or GPUs. We completely isolate them. So if you're not doing something, I'll jump to the next slide. A lot of development workflows we've seen for developing machine learning applications and workflows are designed around Jupyter notebooks. And I know someone spoke about that just before. We generally see that it tends to lead to a significant amount of resource wastage when you run those notebooks on the HPC system. So, it can take hours or days for that job running that to run that notebook to start, at which point you're just sitting there at your desk waiting for it to start. That's not an efficient use of your time. And also, while that notebook's sitting there waiting for your input of what to run, all your dedicated CPUs and GPUs, they're just sitting there completely idle. So that's perhaps not a good usage. And you'll probably get a nasty email from our help desk saying, why is this idle? So this is exactly the same, I think it's 2 talks a day, but consider a hybrid approach. You run your Jupyter notebook on your workstation or in a cloud system somewhere, and there you can analyze your model and test things and whatnot. And then when you want to run a actual big job and train it, you submit that off to the HPC to run in the background, not as part of your Jupyter session. Once it finishes, you've got the results back and you can plot it and make changes to your algorithm or whatever you need to do and resubmit it off to HPC to run again, test it, come back, that iterative process. Now, because each of those is running in its own job, you could need to reread that input data for each job. But for well-structured parallel AI, that's probably not going to be a problem. So that touches back on all of those points sort of touch together into how you can make a good usage of the HPC system if you're developing machine learning workflows. I'm not entirely sure how long that took, but that was everything I put together based on what I've seen.
Interesting how much what we've seen has in common. It's all good that I can get my data into one big file. How does that work with my lovely Conda environment? So I'll let you argue about that in the chat with the other admins. But I will hand over, and I'm going to pronounce your last name wrong, to Guy Lukes to also have a chat to us about HPC.
Thank you very much, Kiowa. I will do the same thing. I'm fairly certain I'm going to butcher a couple people's surnames. If I can ask you to present my slide pack for me, because I'm not going to try and dance with Google, just in case it does give me any grief here. Everyone, thank you very, very much for the opportunity. And I will thank Keeve, Fred, Brent, all of the guys that have presented prior to this, because you've covered a lot of the key components that was leading into this discussion. I have the next slide, Kiowa. So our past, believe it or not, what you're looking there was one of the two supercomputers. This is not an actual photo. I think it was printed on paper and I didn't have a scan of it, that existed in Australia at the early stage of my career. That's a Cray YMP. It was originally 24 bits, then became 32 bits. This thing was capable of 330 megaflops when it started, and it was 2.667 gigaflops when it finally computed. If you want to have a little bit of an idea on magnitude, this one is old and what is in my pocket, but it's capable of between 8.8 and 56.7 gigaflops in single thread, or 23 to about 135 or so gigaflops in parallel. And we used to communicate with them. My board looked much scratchier than that. The CPU board at the top there is one of the CPU nodes, and that was how we used to interface to them. Next slide, please. To where we are today, and there was a whole lot of beautiful talks on Gaudi, but also framing where Gaudi is in the world. Okay, our current supercomputer is running at position number 53 at about November last year, and this is no change in the performance of the machine, just the fact that newer machines have come online. The big one, the Fugaka computer in Japan, is presently the largest and fastest supercomputer in the world that's registered and on the public. The other ones are at Oak Ridge and Lawrence Livermore National Laboratories, and these will juggle up and down through the time. Next slide, please. Now, as my previous presenters spoke extensively, machine learning and high performance computing really comes about how we get things to be done fast. And I couldn't avoid putting at least one Star Trek photo in there. Essentially, we're trying to get our data through some degree of transition into information. I will. That is a lovely photo from the Musée Rodin of Le Penseur, the thinker. I hope everyone actually remembers that and knows these bits. How we go about that, the fantastic discussion on Horvath and all of the Horvath. I do not know if I correctly got the pronunciation, and these ones is where these changes are happening. For the past 10 to 15 years, we have not made significant increases in clock, bus, or CPU. The growth has been a little bit above maybe 15% of a linear. What we have had an increase is in the density, parallelism, and speaking to Brent and the team's previous discussion, how we go about making access and executing on that data. Now, the same way as I hope none of my customers actually expect me to look at anything but a sort of a stunned mullet look if they start talking to me about amino acids, proteins, start-stop codons, you know, it'll just be a blur. However, science has become so specialized, we've narrowed some of the exposure, and this is building more of a requirement of how we can make our infrastructure better for yourselves and many other researchers, not just for the present, but also for the future, and how we can work with you to developing the frameworks and the discussion and how to think about taking apart and parallelizing programs. I will state in my era, this was MATLAB and Fortran. A few of you may still use MATLAB. There are many other old ones that will not be mentioned. And these are the way tools have moved over time. Could I get the next slide, please? This is a really nice example, and I believe Key first spoke to this about when you're running it on an actual machine. Believe it or not, that's a 32 to 64 node baby supercomputer for emulating. It's stacked up with some Raspberry Pis, and 4 Raspberry Pis you can hook up to a GPU. However, if you want to think about and work with an idea, you can build yourself a mini version, or have, you know, your friendly network and computing guy build these for you, and work through and work alongside you and interact in the process of problem solving and taking some of these bits apart. Now, I understand a large number, you probably are on grants and that, so it's sort of a few year budget cycle. For myself, I'm looking 5, 7, 10, 20 years in the future for architecture. Some of our data sets presently are 1 to 2 petabytes. Okay, now whether these are going to be 10 or 40 petabytes, and hopefully there's only small degrees of shock and horror, or who knows, femtobytes, or whichever is the next level up. These are going to be very big data sets, and we're going to need to work together. I know we are very tight on time. I think that's my final slide there, Kiowa. Believe the other one, and I'm not certain whether I'm the last or not, but if I'm not, I will wait, and hopefully we can answer and ask and interact on questions. I will give many thanks. Professor Lindsay Boughton, the previous director of NCI over at Gaudi there, granted me about an hour and a half of his time so we could look at some of where we were in the current world and where some of the future is going. And it was absolutely fantastic to listen to all your lectures and discussions this afternoon. Thank you.
Thank you so much. And thank you everyone for listening. You're right, you are our last speaker. I will grab us in the last 10 minutes to point us all to some links at the end of this, because I'd like to keep talking to all of you, because you've been very interesting. But I would like to open the floor up now for questions, discussions. I see some ranting in the chat about Squash FS and admin rights. I've seen some comments in the chat about, oh, at our cluster, we do Jupyter like this. So that's interesting, because we also do something with Jupyter at our cluster that's different again. Kind of open the floor up. Maybe the raise hand function is in order, because if we all talk at once, we're going to have a hard time. Zoom will not cope. Oh, there we go. We'll keep you talking, Guy.
Cool. Well, I really loved what Fred, Brent, and the others said. But I would be from the day-to-day operations. I would be interested into, some of the lessons learned and some of the rat holes. I will include some links in my final presentation about how you go about thinking and making things parallel. But what are the users actually experiencing, or decision points which may have been easier if they made them earlier? I know that's a how long is a piece of string question, but I'll leave it to Fred, Brent, or anyone who wants to step forward and answer that.
I can say, well, I can't really give you an answer, but I can say some words. What I was talking about is more, it was the path of least resistance that was born out of what was there. It wasn't, I don't really want to say it was designed one way or another, as in I'm a user, and so I'm not the other side, but it's kind of, we have our own restrictions being government and all of that. So it's come from up top. This is the way things have to be. And it's okay, well, within these rules, what can we do? And it's okay, you can use Jupyter on Bracewell on HPC that we have. It's just not nearly as friendly as doing it in this other thing, being that there's not internet access on the compute nodes directly from the outside. So it's like, okay, well, you can like VNC to here, then kind of go into here and bounce through. And that's fine, but then you're in a VNC session, which most people rightly don't really enjoy. And so it's that's why I made the comment about the animal tracks in the forest, because they find the way. And it's like, well, instead of bush bashing through this thing or whatever, just walk on that thing. So it's kind of what I was talking about is something that was just what people ended up doing, and me being a user, I was doing it as well. Like, okay, I can do this here, and then I can go over there because that's easy, instead of struggling with this. So not answer your question, but answer it with lowercase letters, I suppose.
I've got comments to add there, but I see Maxime's followed the rules and put his hand up in Zoom, so I'll let him go first.
Oh, thank you. I have a couple of questions and comments. So I'll first start with the comment. I've recently used more and more a tiny tool which is called Paper Meal, which has been made by Netflix, and oh, sorry. By the way, I'm working at NICI in New Zealand, and I'm helping users to work on the HPC. And that's a tool I find nice to actually take the same notebook that you're using in your interactive environment and actually run it non-interactively. So I feel that's one way maybe to help users to jump on the HPC. And on this note, I have a question for Brent, which is, have you seen some people that stayed on the Jupyter Lab environment, and you knew it would be nice they go on the HPC, but you needed to nudge them, and second question, so then I can stop talking, which is probably for you or maybe for Ben, which is, are you actively monitoring the usage of the GPU in any way, so you can say, oh, this job is not very optimal, maybe we should contact the user and ask them how we could help to make it better. Yeah, that's it for me.
So I suppose I'm tagged first in that, and it's gonna be easy in saying no, because I don't want to do, like, it's not my job, but it's that I may be one of those people sometimes that they need to nudge off. It's not, it is a limited resource. And so there would be times where if I know about something, I would say, yes, let's go over here now and free this up for other people to use. But no, I guess is the super short answer. And that's other people are more concerned with that than myself, which is another non-answer answer.
So on Guardi, sorry, not me, but our user support team look at CPU usage, and generally we'll notice if something's running poorly on the CPUs, but measuring efficiency on the GPUs is not a particularly easy thing to define. So, GPUs are either a kernel is running or it's not running. And that's about as much as it goes. So it's kind of hard to define any other metrics. So we generally don't watch that much.
We kick people off if we see they're doing something really, really crazy, like they're using like a desktop with Google Chrome open on Facebook on a DGX. We'll be like, that is not research. We're kicking you off. And that does happen, right? But it's difficult to tell the difference between that and someone's GPU utilization's gone to zero for a bit because they're reading in data really slowly, right? And that's normal. I'll pass over to Guy. I see you've got your hand back up, and then to Eric after that.
Well, I was just going to add, and my apologies to the people from the Bureau of Meteorology who I may be just tossing under the bus here, but they experience this, I expect, a number of times, because on that path of the bandwidth between your spindles, your CPU, and your GPU, you can frequently stall, and you can get things to run faster by actually running it slower or few copies. And there's a whole, this is where people such as Ben are probably your very, very best friend of speaking to and starting to look through that. But may I use that as a discussion point for any of the BOM colleagues that we have on this?
Hi, Guy. Yes. We really indeed use a lot of I/O, and we in particular we use NetCDF, IDF5, and time to time we find these problems of the I/O, but in general it's not that hard. We use a lot of Dask and Python, so it's not really sharing many things. But what we are finding problem is storing all these single files. And in particular, we have one file every 5 minutes for 66 radar, blah, 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 blah. So we really, really run out of nodes, inodes. So what we're trying to do is just pack everything TARS, move into the job thing, into the local storage, and then run from there, and works much better. Yes, but in general, what we found is at least in Python thing, all the library has to be aligned, in the sense of you cannot be an MPI library fighting with another one, a non-MPI library, and these kind of things. Yeah, so it took us a while to just align all the monkeys, and now we're running out of inodes. So yeah, but anyway, it's an evolution. But yes, I mean, I love the ideas that have been in the chat. Just pack everything and then unpack it when you do the job, and that's it. You solve the problem.
The talk of inodes in relation to ML sort of gives me nightmares. I won't sleep this weekend. I'll hand over to Eric.
All right, thank you. Hi, everyone, and apologies for being in the car, but I need to pick up my son from daycare. It's 5 p.m. here in New Zealand, or almost 5 p.m., so I'm using the last few minutes here. Just to maybe answer a little bit of your question, Guy, and probably a bit of a comment or question for every one of you here in the audience. I'm basically in New Zealand at the Institute for Plant and Food Research, and we do have quite a lot of machine learning and AI and computer vision workloads running in our HPC currently. The vast majority of them seem to be aligned to what most of you have been talking about today, which is what I will call the model development or model training phase of the machine learning pipeline. But the thing that I'm noticing a lot of demand for from our end users is the next stage, the model integration work, i.e. getting a lot of different models working together to answer complicated questions within a particular sector. And also the model inference part or the simulation part, i.e. putting the model into production and then starting to analyze massive amounts of data from industry or customers or science projects. And although there seems to be an overlap in terms of the fundamentals around scheduling the jobs and producing an outputs, the practice and the SLAs are obviously different. So we're actually quite struggling to figure out a model, not in the machine learning model sense, but a service model to accommodate this sort of workflows. And I'm wondering if anybody else here is dealing with the same challenges. How do you move from developing a model and testing your theories and your hypotheses to then productionizing those and creating, API endpoints or web applications, or just running the model to do actual inference on production grade data? Is that something that's common anywhere else? Are we the only ones? Thank you.
Yeah, since no one is taking the question, I think where the angels fear to tread, maybe I would take that question actually. And yeah, so yes, definitely, it is an unfortunate situation in machine learning, both in the industry as well as in the academia. I come from a long stay in the industry, but at the moment in academia, we have been a POC factory. So most of the models are being developed to test an idea, to develop a proof of concept, and a very small proportion of them actually graduate to being deployed on a sustainable basis, and even less so when it really comes to create an impact in the sense. So so there are many models and many more papers, but it is something that we should work towards in that sense. Yes. So to be able to create models that actually create impact is vital, and it's vital for the science, and it is vital for our profession itself. And because we are already seeing a bit of a flag from different business users for impact and so on. That said, yes, I have had the fortune of working on a few of the models that went to end, were deployed in different systems. And so the largest of them is for a Saudi chemical plant that included a number of AIs for predicting deviations, and a number of smaller ones in supply chain, healthcare, and energy, and so on. But the attitude needed for actually developing the POC, I'm a data scientist, so that's what we first think of, is, should really be extended to actually think about finally deploying it. So the problem formulation should actually consider or include the idea of deployment. So I will stop at that and add a student of mine is actually working on that at the moment as well. Thank you.
On the salient point of there being too much discussion to possibly fit into a 2-hour meeting with this many people, I share my screen again. What if you want to keep talking to everyone in this room? What do? You can go to the ML4AU website and contact us. And if you want to put stuff up on that website, talk to us. I can do that for you. I can certainly arrange that. We've just started a Slack space for ML4AU in the last week. Come chat to us there. We can actually keep talking to each other and keep having more Zoom, WebEx. What else are people using? Teams. I don't like Teams. It makes my computer hot. We've got some admins here. I didn't introduce myself at the start of this, but I actually work on the HPC team at the Monash Research Centre, help look after Massive and Monarch. My job for 2 years has been to support machine learning. In particular, we're starting to get a bit of a sub-community of practice to rant about things like people doing weird stuff on Lustre file systems and just how do we help these people get their research done, because that's what we want to do. Email me specifically if you want to come along to our first meeting in March. I'll be picking a date on Monday and sending invitations round. That'll get dumped in the Slack as well for anyone else interested. Another community I'm a part of, which may be applicable to some people here, is the Australasian chapter of Women in HPC plus because we're actually more interested in diversity and inclusion in HPC. We have a lot of people here who are using it. I invite you to join that community as well. I'm on the organizing committee for that. We have a Slack channel where we rant and rave about all sorts of stuff. We have fortnightly Zoom meetings where we rant and rave about all sorts of stuff. But we also write action documents to send to organizations around how can we be more inclusive. So a bunch of links here if you want to keep talking to us on HPC, on machine learning, or diversity and inclusion in sort of infrastructure as well. With that, I'd like to say thank you very much to our presenters who gave their time today to come chat to everybody here. I would also like to thank Tarun and Jingbo in particular, who helped organize this event. I may have done a lot of talking, but they helped with quite a lot of the behind the scenes and got me in contact with some of our awesome presenters. And thank you everyone who's listened and contributed. I hope to hear more from you soon. And with that, I'll let everybody go have their last, oh, maybe not New Zealand, it's a bit late, another cup of coffee before the end of the day if you're like me and you're up late coding. Thank you, everyone.
Yeah, and actually great line of speakers and a great organizing. Thank you, Kiowa, and thank you, Jimmy.
Just hanging out for a bit so people can grab the slides if they haven't grabbed them yet. But I think Tarun will probably email those around at some point as well if you do miss out. If not, sure, if you Google search a name like mine, not many results come up and you'll probably find my Monash email somewhere.
Kiowa, I'll give you an update to that final slide with some links and pointers and other little bits. I'll fill in some notes there. So if you can hold off on publishing, I'll put that in and do that. It probably won't be till later tonight, though, if that's okay.
No rush on our end. The slides will stay in the Google slide format, so people should be able to go look at the link, but not edit everything. So anyone who's still hanging out here thinking they can go edit everyone's slides, no.
Thank you. It was a very fantastic one. I look forward to sitting as an observer in future meetings. Have a wonderful weekend.
Thank you so much.
Now that the room's starting to clear out, I didn't catch the name of the guy who wanted comments on deploying models and those kinds of things, but I thought that was like a really salient point that like should be addressed. I'm not sure if that would be something that ML for AU would be able to do, or yeah, I don't really know anything about that, but that just seemed extremely important if we're not actually able to deploy the models that we use on our systems. So would anyone have like any further comments on that they'd like to discuss? I don't know.
Hey, Nana, you know how we're looking for a topic for Data Science Week?
Yes, that's true. That's true. So, Tim, can you elaborate a bit more? Sorry.
Unfortunately, I can't. So I'm like just an undergrad who randomly ended up on a project in my student team that involved this Horribot project. I'd never touched a supercomputer before, a HPC system before. I'd never even used Linux before. You know, I was a spring chicken who was yet to know anything, and so I've learned a lot over the last few months. But relatively to what I don't like, there's a lot I know I don't know. So I wouldn't really even know what I'm talking about here. Like for some context, I'm studying a Bachelor of Computer Science with a data science major. But it seemed like a very important point if, we're doing this research, but no one's able to deploy their models. I thought it was strange that, well, not necessarily strange that no one had like a good answer for that, but